Hey Alexis, I'm going over topic 10 for you. This is the chi-squared lab. I'm just going to kind of brush over the introduction and what I usually talk about, and then I figure I'll just record the prep meeting tomorrow so you can see what Michael says, and I'll post that too. So this whole lab is just about patterns, like the first lab, and you use them as an ecologist to find interactions. So we're looking at clovers and pennyworts today. Clovers are A, and pennyworts are going to be denoted as B. So you're looking if clovers are present, pennyworts are present, they're both present together, or neither. And that's just to see what kind of distribution they have. So there's 3 different kinds of distribution. There's even, clumped, and random. So even is just, you can look at one organism and know in relation to it where another organism will be. A good example of this is apple orchards. So apple orchards are spaced out so that each tree has just enough room to have enough resources, sunlight and water, without crowding out others. And if they were any closer, they would crowd out and die. And they have to be close enough together that they can have a whole bunch of apples and apple trees, so they're evenly distributed. And then an example of clumps would be like, it's supposed to be Florida. There's a whole bunch of people around the beaches area. I know that doesn't really look like Florida, does it? It looks kind of perverted. But there's a whole bunch of people around the beaches. Not very many people on the inside of the state. So they're clumped around oftentimes resources. So people like to clump in cities, especially because there's a lot of education and arts and things to do, new people to meet, mates, and resources. And so that's clump distribution. And then random, I like to think of cows. You cannot tell where one will be in relation to another. So in the clump distribution that I just talked about, if you can identify a resource, usually you can identify where the organism will be. In random distribution, they might just travel anywhere that they want. It could be some way over here. I don't know if you've ever spent any time around cows, but some will be laying down in a herd by some water, and a few others will be grazing in other areas. There might be one lost. You can't tell where they're going to be, so it's random. So we are doing this lab under the assumption that if the species are not interacting, then knowing the distribution of one will tell us nothing about the distribution of the other. So that just means that they're random. If they aren't interacting, then they're random. So if they aren't around resources, or if they aren't growing in relation to each other, then there is no pattern there, which is why we use the chi-squared. So chi-squared is the summation of the observed I'm running backwards and it's really hard. Observed minus the expected. And you square that. And that's divided by the expected. You probably can't see that very well. Sorry. Here. So it's the sum of observed minus expected squared divided by the expected. Okay, so in our little scenario, how you find the E, the expected, is explained by understanding the sampling design. So we are going to use a quadrat, and it's the PVC square that is used for sampling. 1, 2, 3, 4, 5. Okay, so in this little scenario, the quadrat is used to eliminate bias. So a lot of times whenever I go out and do this experiment, I want to be like, oh, I'm going to go count how many clovers are in this one patch. And you can't do that because that's not really a representative of what's out there. So use the quadrat to eliminate personal bias. And use a random number generator to eliminate bias of going and putting out the quadrat on top of a clover patch. So you'll have a number table and it'll have just random numbers. Let's just say on that number table you pick 91. You will go 9 steps forward and 1 step to the left. And the next time you'll go 9 steps forward and 1 step to the right. But you use different numbers every time. So those are the 2 ways that we eliminate bias in this experiment. But back to the chi-squared. So the expected value is how many times you drop this divided by the number of possibilities. So we dropped this the quadrat 30 times for sunny and 30 times for shady. It's really easy to want to combine the data, but you're doing sunny and shady and comparing them, so you keep all the data really, really separate. So we dropped this 30 times, and so I divide my class up into 4 groups. 2 in sunny, 2 in shady, 1 through 15 does sunny, 16 through 30 does sunny. And we'll just talk about sunny in this little video, but it's the same for both. So anyhow, they drop it 30 times. So it is 30, which is the number of times that you drop it, divided by the possibilities. So in this experiment, you're looking at clovers and pennyworts. So they can be a clover by itself, a pennywort by itself, both of them together, or neither of them present. And for each of these crosshairs, which are called hits, any of these 4 can happen. So it is 4 possibilities, divide that by the number of times that you drop it down. So it's 4 divided by 30, and that equals 7.5. Let's write it down below it. 7.5. So this is your expected value. Okay? So just remember that, and this is how you explain it to them. So now the first thing that you do whenever you're actually doing mathematics for this lab is you do percent coverage. So remember that you're dropping this 30 times. Each of these crosshairs is called a hit. So you can have a total of 16 hits altogether. What that means is whenever you're doing the columns on page 124, I think, 124, there's species A and species B, clovers and pennyworts. Say you see a clover and a pennywort under this one crosshair, that is 1 for each. So the maximum for both of these is 16 and 16. They're going to want to say, okay, well there's 50 pennyworts under this one crosshair. But that's not how the chi-squared works. It's just a yes or no question. O is no and 1 is yes. Is there a pennywort there? Yes or no. If it's no, they write a 0. If it's yes, they write a 1. Does that make sense? So for each of A and B, there's going to be either 0 to 16, but there's not going to be like 35 or whatever. So once they've gone outside and done their data and they have their little tally marks or numbers, they're going to be 1 or 0. For all of these, you're going to calculate percent coverage. So what you're going to do is you're going to have them collect their data together. You're going to I can't think of the word. Not collaborate. Consolidate. You're going to consolidate the data. I like to put it up on an Excel file. This is what it'll look like. So it'll be in these rows down here. And then down at the bottom it has totals. And you're just going to have them added up. So let's just say for species A, there was total of 5 times that there was clovers. For species B, let's just say there was a total of 16 times there was clovers. So what you're going to do is you're going to calculate, well, it's already calculated for you, but how you get the numbers is there were a possibility of 16 hits per throw times 30 times you set it down. And that together equals the bottom number, which is 480. So then you're going to calculate percent for A and then B, for sunny and then shady. So let's just say for sunny it's 5 divided by 480. And then you're going to multiply that by 100 to get your percent coverage. So I'm about to do the math right quick, and we will see. It's 5 divided by 480. Times 100. So that is a percent coverage of 1%. Okay? So they're going to do that for sunny and shady, A and B. So next, what you're going to do is you're going to talk about degrees of freedom. This hasn't really been relevant up until this point, but you need it in order to do the critical value, which is also table 10-1 on page 123, called the chi-squared probability table. For this experiment, it's 3. Pretty much your degrees of freedom is just how many times you can guess wrong before you absolutely have to be right. Let's just say you picked one of these. I could guess 3 times. I could guess A, B, A, and B until the last time, the 4th time, which I had to be right because it was O. Similarly, I can guess a student's exact birthday of the year, whether it be May 12th or July 7th. I can guess 364 times until the 365th time, which I absolutely have to be right. So degrees of freedom is just how many times you can be wrong until you absolutely must be right. And so it's just n minus 1. So it's just the number of times, number of possibilities minus 1. So in this case, it's going to be 3. So that's degrees of freedom. So for the degrees of freedom on the probability table, you're going to go to the number 3. And we use the p-value of 0.05. What that means is just that there is, man, that's really bothering me. I'm having it right backwards. There's just a 5% chance that we're wrong. Whenever we are saying if there's a pattern or not, there's a 5% chance error. Okay, so now the fun part. We're going to actually do our little data. So what I first do is, let's just say there is 1, 2, this is harder than I thought it would be. Okay, 1, 2, 3, 4, 5, and this is in sunny. Okay, so let's just say in 1 for column A, and then column B. Let's just say for 1 you have 0, 0. And for 2, let's say you have 1, 0. For 3, you have 1, 0. And for 4, you have 1, 1, 5, 0, 0. What I have them do is difficult for them. I like to color code it. So I will use different like stars and hearts for you, but I recommend having them do it in different colors, like red or blue or whatever. So if there are neither 0, 0, you can draw a little line. So you go through everyone that has 0, 0, you draw a little line by it. And then every time that there is an A and not a B, you can do a little star. A and not a B, okay. Every time there's a B and not an A, you can draw a heart. And every time that there's both, you can draw an exclamation mark. Okay. So you're using this because for sunny side, you can go all the way down through 30. And I like to do it by, okay, you're going to highlight the ones where there's 0, 0 on both columns. Once everyone's done, then okay, well the ones that are just A, you just have a number in A and a 0 in B. And I like to go through it like that. Otherwise they will get confused. So then I'm just going to count the number of times that there's an A. So in this little scenario, there is an A and a 0 in the other one. So there's just A. It's just one time. Right, one beside it. For B, there's just B and no A. That's going to be a heart. Right, one beside it. Time that there's both, 1. Time that there's neither is going to be 2. So these are the numbers that they're going to be using to have their observed value. So they're going to go all the way through it, through the 30, and their A for their observed is going to be right here. It's going to be the number of times that there's an A but no B present. We actually do not use this A and B together or neither. So I don't know why we haven't calculated it, but we do. So really, they just need to focus on only having A's or B's. So let's just make up some numbers to make this easy to see as far as the chi-squared goes. So let's just say for A, chi-squared, we're going to have the summation of A for sunny and B for sunny. So first we're going to do, let's just say for A, let's just say we did 10. And we have 15 for B. Okay. So for A, it is 10. So it's going to be the observed, which is 10 minus your expected, which remember that was the 30 divided by 4, which was 7.5. So divided by 7.5 squared over 7.5. Okay, so that's for A. So that number is going to be 10 minus 7.5 is 2.5 times itself, divided by 7.5 is 0.8333. Repeating. So then you're going to do it for B. So let's say for B it is 15. It's 15 minus 7.5 equals 7.5 times itself divided by itself 7.5 and plus B, which is 7.5. Okay, and then now you have to do A and B together, and that is, I think I might have misled you earlier by saying they only have to do A and B. They only have to do A and B for percent coverage. They have to do A, B, A and B together, and neither for their chi-squared. I'm sorry about that. So AB, let's just say it's 4. Then O, let's say that's 20. Or, no, let's say that is 1. Okay, so A and B together is 4 minus 7.5, which is negative 3.5 times itself, is 12.25 divided by 7.5 is plus, I'm just going to write it bigger so it looks better. That is A plus B. And this one was 1.6, I think, plus darn it, that was 7.5. And then the A and B together is 1.6. And then 0 is 1 minus 7.5 times itself divided by 7.5 is 5.6. So now to get the chi-squared for sunny side, you're just going to add all these up together. So 0.833 plus 7.5 plus 1.6 plus 5.6 altogether is 15.53. And that is your chi-squared for sunny. So now what you have to do is you have to go to your little probability table on page 123. Whenever you go down the row for number 3, degrees of freedom, and for the P.05 column, your critical value is 7.82. So you're trying to see if your critical value is higher or lower. So if it is less than the expected, the critical value, then it's random. So any number below your critical value means that the distribution pattern is random. Because yours is higher, that means there is a pattern found. So there is, for this one, for sunny side, there's a pattern. We don't know what that is. It would take more research to figure it out, but there's a pattern, which is awesome. So that is chi-squared. I apologize. I know it's late and I am writing backwards, so I'm sure that wasn't super easy to figure out. Just know the biggest thing that I always get hung up on is that for percent coverage, you're counting the number of times you see you see each. If there's A and B together, or 0, and then you use those same values to find, once you find how many there are for A, how many there are for B, and A and B, you use those to find your chi-squared. So chi-squared is your observed, so it's A minus 7.5 times, or squared, so whatever number you found for A, divided by 7.5. And the same is done for AB and B and so forth. So that helps you. I would write that on the board. So chi-squared is the number you found for A minus the expected divided by the expected, pretty much. So that's the lab. I don't think there's anything that I didn't talk about that you would need to know. I will, of course, email you this video and then also the video tomorrow. And I have a little cheat sheet for you that I'll take a picture of and send along with it. Hopefully that will help. And I'm also going to send you my PowerPoint just because I know that you're busy. Hope you have a good time at the conference, and I'm sorry this wasn't better, but I hope it was informative and you feel comfortable now. Okay, bye.